Swayam Prabha. Digital India. Educated India.
Okay, so just to prompt your line of thought, let's just start by saying that you have two profiles P and Q. And I don't know if it is visible, but two profiles P and Q as specified in the statement of the lemma, where we go from P to Q in a way that we only improve the situation of the winner in the profile P. In fact, I'm going to make it even simpler and say let's just consider two profiles P and Q where only the first voter's vote has changed. Okay, so these profiles they satisfy the hypothesis of the lemma, right? So in the first voter's vote, let's say that that's the only vote that has changed, and in a way that respects the position of A, meaning it keeps it either the same or improves it, and all the other votes are in fact the same. Let's just deal with this slightly simplified case, and for the sake of contradiction, let's assume that the output of the mechanism in fact changed to B from A, right? Now, based on the strategy proofness of the mechanism, can we derive a contradiction? So how do you think the first voter, so let's maybe call this preference V1. We call this preference U1. So how does V1 compare A and B? Do you think it's A over B or B over A? Keep in mind that the mechanism is strategy proof, right? Yeah, so V1 better like A over B, because if not, then, okay, somebody at the back, what happens if not? Yeah, so then the voter V1 is tempted to deviate into the profile Q, right? Because if V1 likes B better than A, then she sees that she can change her vote to U1 and actually get B as the outcome, which would contradict the presumed strategy proofness of this mechanism, right? So it must in fact be that A is preferred over B. And here we know that because of the assumption of the lemma again, A must be preferred over B because we said that A's ranking only improves or stays the same. So if A was ranked below B, then we've certainly not respected the requirement of the lemma, which is that A's ranking stays the same or improves. We know that B was ranked below A, and now in the new vote, if A is ranked below B, then A has suffered a demotion for sure. Yeah. So, I mean, given a pair of, so in any pair of profiles, when you see that you can move from one to the other and obtain an improvement in the other profile with respect to the preference in the first profile, then you can interpret the first profile as being your true preference, and then you can see that that leads to a manipulative situation. Right. So V1 has an incentive to manipulate in the profile P, because she can see that she can go to Q and obtain a better outcome. But you're right, there's nothing sacrosanct about P being a truthful profile and Q being a fake profile. That's a temporary status that we assign to the profiles to witness or explain that a manipulative situation has been created. So there are other places where you can also manifest manipulative behavior or scenarios. In fact, can you see one here? Because with respect to Q, the mechanism is giving us B. And now if you consider again the first voter sitting in the profile Q, so this is like a frame of reference thing, so with respect to in the profile Q, now you can see that U1 must be feeling a bit restless, no? Because she likes A better than B in this profile. And what can she do? Does she have an opportunity to deviate in this picture? Right, if she goes back to the profile P, then she can extract the outcome A from the mechanism, which is actually a preferred outcome, right? So that tells us that the first voter of the profile Q has an opportunity to manipulate by going to the profile P if the mechanism outputs B here, which means that we contradicted the strategy proofness of the mechanism, and therefore it cannot be that the outcome of F is different in the profile Q, because this holds for any B different from A. So it must be that F of Q is also A. Yeah, is that reasonable? So we have monotonicity, which is so the second claim I want to make is about Pareto optimality. So let's say that this is sort of trying to transfer unanimity. So suppose we have a profile P where everyone prefers A over B. So remember that that's the unanimity setting that we were talking about in the context of social welfare functions. Here what we want to say is that the candidate that is ranked lower between the two cannot actually win the election. Okay, that's a natural analog of unanimity in the social choice setting. And we can in fact derive it from strategy proofness. So I forgot to say that for So if your function f is strategy proof and onto, which as I said will be something we assume throughout, then it is also unanimous in this sense. So again, let's pause here to think about why this would be true. So again, just to get you started, think along the lines of contradiction. Strategy proofness would mean that, yeah, in every profile for every voter, it is the case that there is no other profile where all the other votes are the same and her vote is different and the outcome of the mechanism is better than the current outcome. Sorry? And they can hope to change, yeah. So if, I mean, yeah, so no voter has any incentive to deviate in any profile. If you don't think about dictatorship, you're saying, well, I mean, we are, of course, trying to prove that other than a dictatorship, such a mechanism doesn't exist. So, I mean, I'm sure what you're saying is correct, but I don't see it as transparently as you are. So, okay, let me just clarify what I mean, I guess. So, you have maybe the space of all profiles. Okay. So, this is just a rough sketch to illustrate what we mean by manipulation. It also perhaps, I mean, I was going to get to it at some point, but it also perhaps will illustrate that although it sounds reasonable on the one hand, the property of being strategy proof is actually in some sense also demanding. So let me just project my attention to all the profiles from the point of view of a particular voter I, yeah, where all the other votes, let's just have an arbitrary but fixed choice for all the remaining voters' votes, okay, and let's just say that I's voters, I mean, we are looking at all of these profiles where, so I have drawn 5 here, let me make another dibba. So let's say there are 6 candidates and I'm focused on, so this could be ABC, this is ACB. So these are the 6 possible orderings that the voter I can have, okay, and the choice of the remaining voters is arbitrary but fixed. So there are, you will get a bunch of different slices like this if you focus on the voter I. Okay, so what I'm saying is that sitting inside any one of these profiles, okay, and looking at the outcome, so let's say here the mechanism outputs A, okay, there is no other profile in which the mechanism outputs B, for instance, right? Because then voter I would have an incentive to change their vote accordingly and nobody else would have to do anything. She would not have to convince anyone else to join her strategic agenda because all the other votes are fixed to be the same. So manipulation is simply saying that if F outputs A here, then F should not output B on any of the profiles. If F outputs C here, then F cannot output A or B on any of the other profiles. But if F outputs B here, then F is free to do whatever it wants on the other profiles, because whenever F outputs the top choice of any voter, the voter anyway does not have any incentive to deviate because she is getting her best option. Okay, so this is what the property means. Yeah, and I think what you were saying is that this, I mean, how can a voting rule manage to keep track of all this? And Yeah, so in every profile there are always going to be m-1 losers, right? And there will presumably be voters who are rooting for them, who like them better than the current candidate, unless the current candidate is really a hot favorite and is on the top spot for all the voters, which is probably what you were alluding to. So somebody, yes, it is true that for the m-1 losers, it is quite likely that there will be someone who is feeling bad about at least one of the losers and would want to move to a profile where they can make that person win. But what we want from the mechanism is that they should not have an opportunity to do so. So if the mechanism itself is such that it's kind of stingy about, or it has so much structure that, so for instance, as we were saying here, if for instance in this profile, you know, A was winning, if the mechanism just outputs A or C on all the other profiles, at least the voter I does not have an incentive to change her vote, right? So basically what we are saying is this is one condition, and you will, you know, basically based on what you decide to do on one profile, a lot of constraints will emerge, right? Right, but this is not the entire set of profiles. This is just 6 of the profiles that I've gotten by fixing the remaining votes. If I change the remaining votes, I will get a whole bunch of other profiles. Remember, the set of all profiles is so 6 raised to the number of voters n, right? So, so there are very many more. I've just fixed on, I've fixated on 6 by fixing a choice for all the other voters' votes. But when I change those choices slightly, I will get another layer, I'll get another layer. So there are, I mean, many such slices. And I've given you the conditions for strategy proofness based on the slices generated by focusing on the voter I. If you focus on a different voter J, you will be slicing this space in a different way. You'll be getting a bunch of other slices and a whole bunch of other conditions, right? And these conditions are all in the form of, okay, if you decide to declare A as the winner here, then you should be careful about not declaring, you know, so and so as a winner in so and so profile. So you get a whole bunch of these conditions, and any mechanism that manages to satisfy all of them is called a strategy proof mechanism, right? Exactly, yeah, yeah. So, right, I mean, so first of all, losing candidates themselves cannot do anything. Whatever they have to do would have to be via the voters who support them, because candidates don't even have votes to play around with. But if there is a losing candidate and there is a voter who is rooting for that losing candidate, as in this example, for instance, for the voter I, B is losing and B is actually her favorite candidate. So if she could help it, she would really like B to win. But in all the profiles, she investigates all the other profiles that she can legitimately go to. Any of the other profiles that I have not highlighted here are not accessible, because other voters have changed their votes. She would have to knock on their doors and ask them to also change their votes. We are only looking at the single voter manipulation case at the moment. So these are the only profiles that she can actually access by changing her vote. So these are the feasible profiles that she could move to. But sitting on, you know, sitting in this island here, looking at all the feasible profiles that are within her reach, she sees that all of them are pretty futile. No matter where she moves, she is not going to be able to make B win. And in fact, in some of them, the outcome will become even worse from her point of view. So she really might as well stay put. Yeah. So does that address it in the way that you were indicating? Yeah. This makes sense? But yeah, whatever we are going to be arguing now is going to be indicative of the fact that this really is too much for a mechanism to keep track of, and that if it also wants to be onto, then in fact it will not be able to be strategy proof at the same time. But that does require an argument. I mean, it's not something that follows immediately. But certainly if you relax ontoness, you can probably come up with non-dictatorial mechanisms which are strategy proof. I'll let you think about that for a bit. So let's just come back to the issue of unanimity as seen in the context of choice functions. So what we were saying is that if a mechanism is strategy proof and onto, then it also respects unanimity. Meaning that when everyone is saying A is better than B, it doesn't go and pick B as the winner. Okay. And again, let's try to let's try to think of this by setting up a contradictory situation. So suppose the mechanism indeed screws up and decides to make B the winner in a profile where everyone is rooting for A over B. And let me just say one more thing and then pause to think. Because the mechanism is onto, we know that A, which is the candidate that we are fighting for, must be winning somewhere. I mean, sadly, it is not winning in the profile where it makes sense for it to win, but because the mechanism is onto, it's compelled to make A win somewhere, right? So there does exist a profile Q, which, because of our assumption here, is different from P, where A is winning, right? So we've set up these two profiles, something that we derive immediately from ontoness. Now can we do some maneuvering to derive a contradiction? Again, using the fact that, so we haven't yet invoked strategy proofness, but let's just stare at this for a minute or so and then we will. So remember that we also have monotonicity, where we said that if we promote everyone, then the outcome does not change, right? I don't know if I said that quite right. What I meant to say was that monotonicity tells us that if you take a particular candidate and leave them alone or you promote them, and if they are already winning, then they continue to win. That's what we want to say. So maybe let me just put this up for your consideration. Consider a profile where what we have done is we have dragged A and B to the top and the second positions, and for the rest of the candidates we are just imitating the profile P. Okay. So essentially imagine just taking the profile P and in one step promoting A to the top position everywhere, and then in the second iteration promoting B to the second position in all the votes. So what can you say about the outcome in this profile? So what happens if you apply monotonicity with respect to P? So B was winning in P, and all we did was we promoted candidates. So in particular what we did was we promoted the winning candidate B up to the second position. So B's position, okay, so if you stare at P and this auxiliary profile that I've created R, the hypothesis of monotonicity was that the winning candidate's position has not become worse in any of the voters' votes. Is this true? This is true because B certainly did not have a first position with respect to any of the voters, right? Because we know that A is preferred over B by everyone, so B's best possible position was at the second spot for any voter. And what we have done is we have placed B at the second position in every voter's vote. So certainly B's position has not worsened with respect to any of the voters. Yes. So the hypothesis for monotonicity does apply, which tells us that the output in R should be B. If you apply monotonicity between P and R and look at the winning candidate in P, which is B, and realize that B has not suffered when we transition to R, we see that by monotonicity, which is a property guaranteed for any strategy proof and onto mechanism, F must output B on the profile R. On the other hand, what else can we do? Remember that we are trying to drive a contradiction here. So what else can we analyze? So along these lines, can we also say that F must output A on R? Is there some reason for that? Because if that happens, we have our contradiction. We know that A and B are distinct candidates and F is a function and it must really make up its mind on what to do in R, right? Sorry. So is there a reason that R must output A, let's say by monotonicity or any other reason that you can think? So unanimity is something that we are trying to prove. So we are trying to say that if, so I suppose what you're saying is that if everyone places A on the top, then by unanimity, F should output A, which is a tempting thing to say, but we don't know that F is unanimous. All we know is that F is strategy proof and onto. So, but we do want to say that, I mean, that's a conclusion that we will eventually derive. Would it be possible to apply monotonicity with respect to Q and R? We have already applied monotonicity between P and R to argue that B must emerge as the winner, right? Because we said that B's position does not deteriorate in any voter's vote when moving from P to R, between the profiles P and R. So who is winning in Q? A is winning in Q. And can we say that A's position has not worsened in moving from Q to R? Yes? Why can we say that? Because A is in the top position, which is the best that you can hope for any candidate, right? So A has the best possible position in every voter's vote in R. So even if A was winning in Q because Q was very generous about putting A on the top for every voter, even then in R we have not made things worse. And if that was not the case in Q, if anything, we have improved A's situation with respect to every voter. Okay. Every voter that did not place A on the top now places A on the top. So certainly between Q and R, the movement for A has been in the positive direction. Right? So because A has the best, in absolute terms, the best possible position that it can enjoy for every voter with respect to every voter's vote. So applying monotonicity between Q and R, we conclude that the mechanism must in fact continue to output A, which is something that it was doing on the profile key, right? So that is your contradiction, because applying monotonicity between P and R, you see that the mechanism should output B, but applying monotonicity between Q and R, you see that it should also output A, which is a contradiction, yeah? So you also get unanimity from strategy proofness and ontoness, which is, I think, yeah, just interesting way of relating different properties. Now remember that our original statement was about combining the properties of being onto, strategy proof and non-dictatorial, and saying that that's an impossible combination, right? So again, I'm going to try and illustrate this with an example, and I did think that I'll do a proof with 2 voters, but depending on how this goes, that is something that I may actually defer to a tutorial problem, so we'll see. But at least to get some intuition, let me just put down an example here. So okay, so let's consider these 2 profiles here, where C is ranked at the bottom for both the voters. So I'm really focusing on profiles with only 2 voters and 3 candidates, which is kind of the minimally interesting instance. If there's only 1 voter, then the voter is trivially a dictator, and we know that we need at least 3 candidates to play around with from the assumptions of the statement. So it's really the smallest kind of example that we can consider that would still be interesting. So in the first profile, so again we are considering, I mean in the backdrop it's always a onto and strategy proof function that we are considering, which by now we also know satisfies also monotonicity and Pareto optimality, or it satisfies unanimity. Okay, so so in the first profile, being unanimous, can the outcome be C? Can the outcome of this function be C? So C is ranked at the bottom by both the voters. So since all voters prefer A to C and all voters prefer B to C as well, I mean on both of these counts you cannot output C, right? So we know that it is between A and B. And now I'm going to say suppose the outcome is A, okay. Then in the second profile, where A was demoted to the bottom position by the second voter, can this outcome be B? Just think about everything you have at your disposal. So can we again say that it must be A or B, and in particular it cannot be C? Why can't it be C in the second profile? B is okay. So C is never anyone's first choice, and in particular, both voters prefer B over C, and the rule is unanimous, right? So it cannot output C. So again, we know that it's between A and B, but in the previous profile, the mechanism outputs A. So in this new profile, can it output B? So remember that the mechanism is strategy proof. So do you see a contradiction based on that? Right. So the second voter has an incentive to deviate from the profile P to the profile Q because she likes B better than A, and the second profile is giving her a better outcome from that point of view, and the first voter's vote has not changed. So by changing her vote from BAC to BCA, she can extract a better outcome from the mechanism. So the mechanism, in the interests of being strategy proof, is compelled to output A here. Because of unanimity, it cannot output C, and because of strategy proofness, it cannot output B, so it must output A. Okay. So intuitively, notice what is happening is that the mechanism is spewing out A in spite of one of the voters ranking A at the bottom. So we have, again, here we see that A is a polarizing candidate. One of the voters has ranked it at the top and the other voter has ranked it at the bottom, which seems to indicate that in some sense the first voter is a pivotal voter for the candidate A, right? Because even though the other candidate is saying no dice, sorry, the other voter is saying no dice for the candidate A. She has ranked A at the bottom. But by placing A at the top, the first voter managed to force the mechanism to output A, right? Again, this is not a proof, but essentially so this proof at this point is in spirit not very different from the kind of arguments that we were making in the case of Arrow's theorem, but essentially, you could also derive this from monotonicity, right? So if A is the best outcome for one individual and is the worst outcome for another, as long as this individual votes and the mechanism outputs A, as long as this individual keeps A at the top, whatever else happens, A's positions are only going to improve if the profile changes anymore, right? So I guess what I'm trying to say is that if you have a situation where there is one voter who places A at the top and the remaining voters place A at the bottom and the mechanism outputs A, then this voter is pivotal or dictatorial with respect to the candidate A, because in any other profile, if F is giving you A here, in any other profile, A's situation either stays as bad as it is now or it only improves. So by monotonicity, you continue to output A. As long as the first voter continues to just say A is my favorite, right? Then basically this was the worst case profile where you managed to derive that F outputs A. So in any other profile, F will continue to output A, and therefore it's really only the first voter's vote that counts as far as A is concerned. So what you really need to show is that, again, similar to before, you need to show that you can actually find these pivotal voters for every candidate, and that these pivotal voters coincide and they are essentially the same voter, which will lead you to your dictator. And all of this can of course be made quite formal. I'll try to break this down a little bit so that it can be addressed as a nice tutorial problem. So it should not be hard to formalize this argument based on the practice that we already had with Arrow's theorem. So I just want to spend a few more minutes talking about where we stand and what are the consequences, or rather what are the workarounds that we can imagine for this impossibility result. So we saw Arrow's theorem, and then we say, okay, maybe welfare functions are too demanding a situation. So we relaxed our setting even and came down to choice functions. But even in the context of choice functions, we have seen one fairly dramatic impossibility result, which says that with ontoness, which is a very fundamental property, and strategy proofness, which again, just like IIA, you could sit and debate till late hours about whether strategy proofness is something that you really want to demand or whether it is too strong. I think some of you already have an intuition for why it's perhaps too strong a demand to make. But if you do ask for these things, then again you are stuck with dictatorships. So now we really must sit down and think about what is the next best thing that we can hope for. Is this to say that every reasonable mechanism, which is to say, let's say every mechanism that is onto must either sacrifice strategy proofness or sacrifice being reasonable, which is, I mean, to say that it ends up being a dictatorship. Of course, that's what the statement of the theorem is saying, but let me propose a couple of workarounds that actually do not really work. One is to say that you move beyond deterministic functions, right? So you introduce some randomization, so you expand the class of things that you're looking at, and maybe you can actually take some help from randomization to sort of say that you can do better than what the impossibility result claims. And I'll not make the formal claim here, but it turns out that randomization is something that is not very helpful in this setting. The other kind of thing that you might ask is, again, going back to this collection of profiles. So let's say, right. So strategy proofness is basically saying that no voter has any incentive to manipulate in any profile, right? That's, I mean, now that I'm putting it that way, it's sounding pretty strong as well. So let's just say that, let's just mark the profiles which are vulnerable to manipulation by some voters, and let's mark the profiles which are not vulnerable to strategic behavior. So these are the strong ones. Of course, this breakup depends on the mechanism F, right? So fix a mechanism F and look at how it partitions the space of profiles into those that are vulnerable and those that are not vulnerable. So I go to a profile and I ask, well, is there any voter here who has an incentive to deviate to some other profile? If yes, then I flag it as something that's a dangerous profile, or it's not a good profile for this mechanism. And the green ones are where you see that they are not vulnerable, right? And what we are saying is that we declare F to be a bad mechanism or a mechanism which is not strategy proof if there is even just one red profile, right? Even then we are unhappy, right? But perhaps we can be a little more relaxed about this whole thing and say that I'm happy if there are a small number of these flagged profiles, right? So if by and large on most profiles the mechanism is not vulnerable, that's probably good enough for me, right? Yeah. Okay, so it turns out that this is also something that people have investigated more closely, and this is what is called quantitative versions of the Gibbard-Satterethwaite result. And the attempt is to sort of understand the degree of vulnerability to manipulation via which the extent to which F is close to being a dictatorship, okay? And the overall theme is that, so for a dictatorship, the set of red profiles is simply empty, right? There is, there are no vulnerable profiles at all, because in every profile nobody has any incentive to manipulate, right? Now if you want, the smaller you want the red set to be, the closer you have to go towards being a dictatorship, and this is something that can be made precise. I don't want to again state the actual theorem here, but I just want to say what I mean by distance from a dictatorship. That's because there are many notions of distance that you can define between functions. So you can here the distance, at least in some versions of the theorem, the notion of distance is simply the number of places where you disagree, right? So you can, okay, so let me just get rid of this. So a mechanism F is something that simply partitions the profile into at most m classes, right? So these are, so let's say you have candidates A, B, C, D. So here are the profiles. These are the profiles where C is winning, the top left are the profiles where B is winning. So every mechanism is just a partition of the profiles. It's a labeling of the profiles with candidates, right, based on who is winning in that profile. So I've just collected together, in this region I've collected all the profiles where B emerges as the winner with respect to F and so on. So if you give me two mechanisms, let's say F and G, the distance between these two mechanisms is the number of profiles on which F and G report a different winner, okay. That is their disagreement distance. So let's say that we have F which comes up with this partition, and let's say we have G that comes up with, maybe it's exactly the same here. So this is a slightly different partition. You can see that you know, on these profiles, F is reporting B, but G is reporting A, and so on, right? So there are profiles where these two mechanisms feel differently about who should win, okay? And that's the distance between two mechanisms. It's the number of profiles on which they have different output. And of course, dictatorship is not just one mechanism, it's a collection of, if you fix the number of voters, it's a collection of n different mechanisms. So the distance, so your proposed mechanism, the distance from dictatorship is basically which dictatorship are you the closest to, that is your distance, okay. So you can also define, again, I think maybe I'm going through this too fast, but so dictatorship is not a single mechanism, right? There is one for every voter. If you're going to mimic the first voter, then that is one mechanism. If you're going to mimic the second voter, that's another mechanism, and so on. So, so this is a bunch of mechanisms, and you know that anything that is onto in strategy proof actually coincides with this class. And if you are a hopeful mechanism that's trying to optimize the number of profiles which are vulnerable to manipulation, well, I'm going to look at how far are you from each of these dictatorship functions, and I'm going to say that your distance from dictatorship is the smallest of these distances, okay? Which sort of makes sense, because you're saying that there is a dictatorship with respect to which you are almost in agreement with this dictatorship, then that's what I'm going to count as the distance. And as I said, the spirit of the quantitative version is to say that the more you want to avoid the flagged profiles, the fewer vulnerable profiles you want to have, the closer and closer you must tread into the domain of dictatorial functions, okay. So, so if you are an interesting mechanism that, you know, looks very different from any dictatorial function, the price you have to pay is that you must suffer a substantial proportion of vulnerable profiles, okay. And I think people have really dug fairly deep into this, because even within the vulnerable profiles, you could imagine having degrees of vulnerability. Maybe there are profiles in which only 1 or 2 voters have an incentive to deviate, versus there are profiles where many voters have an incentive to deviate, and things like this. But at this point, the literature does get fairly intricate, but it's also very interesting. So the space of profiles that I'm talking about has some very interesting geometric interpretations and their relationships to an area called the analysis of Boolean functions. So it's all very, very interesting. Unfortunately, it's also well beyond the scope of our current discussion. But if anyone is interested, we're going to put up references on the website for today's schedule. So do check it out. There is a lot going on in this context. Okay, but as I said, these were two of the things that, so the quantitative versions and appealing to randomization are two things that seem natural, but they also don't work. So it seems like my narrative is just getting sadder and sadder by the minute. So we're going to try and see if we can pull ourselves out of this by looking at things that potentially do work, which is to say that so when we come back, we will look at a couple of approaches that turn out to be actually reasonable. One is to say that maybe we don't really need to worry about the space of all profiles. This is a humongous space, and maybe we are just asking for too much. So maybe there's a little thing that we can carve out for ourselves where it all looks nice and green, and maybe we can carve out a space which is actually also sensible, meaning that we might say that most instances that you deal with in the real world, most profiles that come up in real world scenarios actually have the structure that we identify. So if we can do that, then that's something that would be a reasonable success, I think. So we're going to see if we can carve out a structure that makes sense in this fashion. And the other thing is to say that, well, when we talk about strategy proofness, we are giving a lot of power to the manipulator. In particular, it's one thing to say that you are vulnerable to manipulation on paper, right? If we go back to the picture that your question prompted, so here for instance, here is a voter I who is probably thinking about manipulation, but we are assuming that the manipulator actually has complete information about what all the other voters are up to, which is a pretty strong assumption. There may be all powerful manipulators in some small voting applications, like let's say it's a small committee that's trying to figure out who wins the Oscars. Then maybe you could assume that they're all friends and they know, they roughly have a sense of what everyone else is going to be voting. But in most larger scale applications, this is not such a reasonable assumption. And the other assumption that we are making is that it's just enough for us to know that manipulation is possible. But for manipulation to actually become an issue in real world instances, you would want the manipulator to have a systematic way of figuring out how to manipulate. Just knowing that you are sitting in a profile that is vulnerable is not enough. The manipulator needs to be able to figure out what I should do to be able to actually successfully derive a better outcome. So we have been again working this out in ad hoc fashion. For a few examples, we did that a little bit yesterday. But coming up with algorithms for manipulation may not be easy, and that is our other glimmer of hope, that maybe even though it's a problem on paper, in practice manipulators may have a hard time figuring out what is a good strategy. So those are the two things that we will come back and talk about on the other side of the break.